Hello everyone. Good evening to everybody. Welcome to our today's session. Yesterday we were discussing about. So we have finished linear regression, and we have also started with our. Yesterday we had also started. 1 second. What was the last topic? This linear regression was done. Started with the logistic regression. Seems to be 1 second. Okay, we have done linear regression, I guess. Yeah, that's the one which we have discussed. This is your URL link for the material. Okay, you can access it. So wondering, did I discuss the logistic regression? Not yet. The last topic that we covered yesterday was linear regression, seems like. Yeah. House price prediction is what we have covered yesterday. We'll start with the now classification model. So we'll start with a hands-on session, but before that, let's understand the model. We start with the logistic regression. Let us start with this logistic regression part. Now let's start with our introduction part. Let's discuss. So this classification problem, we try to identify the problem as a classification problem. And what are we trying to achieve is that we have a classification problem, and we need to check that when your independent variable, or which is known as your features part, let's take the features here. So these features, they are continuous. Okay, they should be continuous mostly, but most importantly, the dependent variable should be categorical form. Okay, they should be like two categories or more than two categories. Ideally, for logistic regression, we expect that we should solve it. This model is really good when the label is binary classification, though this can also work good for multi-class classification. But yeah, that's how the things are. So in this case, we are expecting that our label. Hmm. We have a label which is represented as yes or no. We have a label which is represented as yes or no. This is your categorical form. So our classes are represented as a positive class and a negative class. Let us take a real life example of classification, and it will be used to categorize the mail. For example, it is used to categorize the email as a spam or not a spam. So here we go. This is to categorize the email as a spam or not a spam. Spam or a not a spam to categorize. So this is your example. So we categorize the mail as a spam. And further, we have got no spam. So this is your spam and not spam. Similarly, we can have label churn. Churn indicates as a yes or no. What is the significance of churn here? The churn means when the data for a given data, the custom it indicates how. So this is gonna show churn equals to yes or no. This churn is basically indicates if a customer is using a services or is not using a services. So this is your two class classification, or also known as binary class. Next, we are having a tumor which is represented as malignant or benign. This is where we can see that the tumor is categorized as malignant or benign category, or the transaction is known as fraudulent transaction or genuine transaction. So here all problems are answers in a categorical format, which is represented as yes or no, and that is why they are two label or two class classification. Let's go ahead. Here comes the classification problem. Let's talk about a simple problems. You see that we have the classification problem. Let's imagine that you are a store manager at Apple Store, and this helps you in increasing the sales by 10%, increasing 10% of the sales revenue. This is what we achieve as your goal of this month. Therefore, you need to know that you are, I mean, the store manager wanted to know if you are a potential customer to purchase an Apple product or not. For that, he hires a data scientist and he has been given a task to classify the data. So, with the features, with the information that is available for the customers, like for example, we have got the customer ID or user ID, we have been this is available. We are also having customers age as an information, customer salary is there. Okay, we have all these informations with you and customers gender as well. So we are having all this information. We have the customer's gender. We have the customer's gender. Now the gender is represented as of course male, female. Now we just let's identify here all these features and let's just come to the conclusion part. When provided with male and female part. Okay, let's come to the conclusion. When your we have informations like when your user ID has been provided. Let's see the information. We have got age of the customer as 48, salary 41,000, and gender is male. The label is yes, the person has purchased the product. Similarly, when the person is recognized here as female, okay, so let's take it female with user ID information, age of the female, and the salary or income of the person, and the label or we have the purchased power is represented as no. Similarly, for this also it is represented as no. Okay. Now in this case, in order to maximize the sale amount, the client information you have is including the estimated salary, gender, age, and customer ID. And according to this information, we feed into the model, and we are expecting that this classification model should able to predict for a new sample data. And this is how the new sample data is represented. The new sample data that you see here is having gender equals to male. We have gender equals to male, age is 37 years, and salary is equals to $67,000. These are all your informations which are available to us, and this help us in getting the category as the person has purchased the product or has not purchased the product. If this is what we are expecting after model has got trained with these number of random sample data, and then it is able to predict that for this new sample data whether the person is able whether the person purchased the product or person has not purchased the product. So these are all your informations which is available to us. Okay, now that we have understood all this part, let's go ahead. Let's move to the next part. Let's just start with our introduction to the logistic regression. Now, let's start with our definition part. Logistic regression is defined as one of the classification algorithm which is used to assign observations to a discrete set of labels or classes. In this case, logistic regression transforms its output using logistic model. So one it uses is the logit function, which is also known as your logistic function, and the other one is known as sigmoid function. So to return a probability value, which can be mapped to two or more than two discrete labels as the responses. Now let's continue here. Definition once again. Logistic regression is your again, this is one of the supervised machine learning algorithm. So we have got this supervised machine learning algorithm, classification algorithm, which is used to predict the probability responses, the probability of a categorical dependent variable. In logistic regression, the dependent variable is a binary variable that contain data which is represented as 1. The label is represented as 1, which indicates which is represented as yes or success. Further, we have got 0, which is represented as no or failure. In other words, logistic regression model basically predicts the success, which is basically represented as a function of x. Okay, so you can see that it is basically represented as something like this. You try to find out, you try to predict probability of success like this. So you take probability of success. You take probability of success, and you can also say that it is basically representing your probability of y for the given input data x. That's why you can see that it is represented as a function of x. Further, let's move ahead. So that's how you represent, but how does we are able to get the probability as a response? That what is the likelihood that the output will be 1 for a given value of x? You don't solve for probability for y equals to failure or y equals to 0. You only check it for the failure part, success part, and not for the failure part. Now let's see here about the logistic regression last part, where we are having customer prefers brand A or brand B. Next, employee opt for to choose work as for full time or part time. Next is loan is delinquent or not delinquent. Person viewed in the last election or zero. So these are your responses. Now here comes the hypothesis equation. This is the hypothesis equation which is used by the model to give you the output responses. Hypothesis of logistic. It is represented as probability of y equals y for the given value of x. So the given by or is represented by e to the power beta naught plus beta 1 into x upon 1 plus e to the power beta naught plus beta 1 into x. What is this beta naught plus? This is basically your linear regression equation. This is basically representing the linear regression equation part. Now let's go ahead. The logistic regression model that we know. This is simply a nonlinear transformation of linear regression model. The logistic regression is represented as an S-shaped distribution function. Why S-shaped? Because when you will start plotting it, that is, when you start plotting the probability of y of success for the given value of x, when you start plotting it, it will give you an S-shaped curve. Okay, I'll show you how it looks like as we'll be proceeding further, but that is why it is mentioned that the logistic distribution of these probabilities for the different values of x, they basically represents the it is represented here as shaped curve, now which is similar to standard normal distribution constraints. Now you check it here, you check the responses estimated to lie between 0 and 1. Now let's start with our assumption of logistic regression. Let's start with our assumptions of linear regression part. Now here comes the assumption of logistic regression where the dependent variable we have got the dependent variable. Now one of the important thing is that just remember that your outcome or the label it is represented as y equals to 0 and y equals to 1. Let's talk about the ratio of cases to the variable. Remember that these discrete responses, that is y equals to 0 and y equals to 0, logistic regression will only fit better when you are having enough number of samples for every given category. Okay, most preferred is that we should have equal distribution for class 0 and class 1. Both should be equal. Okay, so we should have enough number of responses for every given category. This also assumes that the independent variables that are linearly related, no, it should be linearly related to log of odds. What is log of odds? So again, odds is a very important statistical term, which is basically also known as odd ratio. And what is this? This is basically represented as probability of success upon probability of failure. So if P represents probability of success, 1 minus P will represents probability of failure. So it is ratio between P upon 1 minus P. So if you will try to, so linear regression basically shows a linear relationship. These features, independent variables, there is X value represents a linear relationship between the log of odds. That is, if you take the log value of odds ratio between X and between this, linear regression assume that there will be a linearity. Again, as we progress further, you'll able to see this and you'll able to understand it in a much more better, clear manner. This equation is not a linear equation. This is known as sigmoid equation, by the way. This is known as sigmoid equation. And the simplified version of this equation is 1 upon 1 plus e to the power minus z, or e to the power minus beta naught plus beta 1 into x. 1 upon 1 plus e to the power minus beta naught plus beta 1 into x, or this is also known as minus z value, minus z value. So it's represented as where z is equals to beta naught plus beta 1 into x. Next is if there are too many cells with low responses parameter, estimates as it is gonna blow up the error here. By the way, in this case, the error will be also different. Remember, it won't be the error where you have to, you know, take the residual between the actual value and the predicted value. But in fact, the error will be in this case represented as binary class classification error, where we need to check. So error in this case will be represented when your actual value is not predicted as represented as your predicted outcome. When your actual outcome and predicted outcome is not same, then only it is considered as then only it is represented as what is your error. Linearity part I have already discussed. Linearity is basically represented by the logit function from where the name has arrived. I will explain you as we progress. Now, this is important. Just like the linear regression model, this also represents that. This also not represents this. No multicollinearity. There is no perfect multicollinearity which is which should be present. as all variables, we are expecting it to be of independent variables type. No, logistic, there is no influential. Okay, it is also expecting that for all the various features value, there has to be no outliers present. Okay, next is logistic regression is good for two classes. If it is more than two classes, that means if it is, there are two type of classification problem. One is binary and the other one is multi-class classification. Let me explain you. Binary classification means these all examples that we are discussing. Binary classification means when we are having responses yes or no. Next is multi-class classification. In multi-class classification, the responses will be represented as when you are having labels as 0, 1, 2, 3. So we have got this multi-class classification. Now let's just talk about here problem scenario. So we had the spam and not spam thing, or employee loan is delinquent or not delinquent, whether these are all yes and no thing. But let's say that I wanted to find out category of heart disease. So when you wanted to categorize as per the heartbeat, the category of heart diseases, then in this case there will be 5 category. So we'll be representing it as 0, 1, 2, 3, 4, 5. There are 5 categories of heart diseases which are there, like one is normal heartbeat, then we have supraventricular, ventricular, okay, fusion heartbeat. These are your details, or we can say category of heartbeat. Okay. Similarly, you can also talk about classify sentences which can be classified as 3 labels. The tone of the text could be normal, or you can say neutral. The tone of the text could be is a positive, and tone of the text is negative. So we are having 3 category of sentences, which is represented as neutral sentence, positive sentence, and negative sentences. Okay, so if more than 2, then it is multi-class classification. If it is 2, then it is just 2 categories. Okay, let's continue with our equations. This is your quite a known equation, which is linear regression equation. We have already learned about it yesterday. Beta naught plus beta 1 into x1, beta 2 into x2, beta n into xn. That's your multiple linear regression equation. Now, but we cannot use this equation to identify the label of a data set. Okay, This is good for predicting the value, okay, the continuous value. It is not good to predict if there will be a label 0 or label 1 for a data sample. Now let's represent the hypothesis equation of the logistic regression, which is represented as h of beta x, or probability of y for the given value of x is represented by 1 upon 1 plus e to the power minus z, where z is beta naught plus beta 1 into x1, beta 2 into x2. This is how it is represented. Now let's continue here. This is how the logistic regression actually looks like. Now you see here, this is how the responses are generated. We have probability for y equals to 1. Probability of success for the given value of x. This is what has been provided us. And this is all about your label 1. This is about your label 0. Now for every given, so what basically it has done is that it finds this equation actually returns you probability. This is your, what is this equation known? It is known as sigmoid function. This returns probability. This is this returns probability of output. Probability of output equals to 1 for given value of x. That's how the things work. Now let's continue. This is how all the samples will look like. If you look at here, on all these points that you see, they basically represents probability of success for given value of x. You can also say that it is represented as probability of y equals to 1 for given value of x. This is how it is representing. And the formula that it uses, 1 upon 1 plus e to the power minus z. This is how it works. So this is your S-shaped distribution, which is represented by your which is represented by sigmoid function. Now I like to remind you, remember I discussed here that it shows, where is it? S-shaped distribution. Yeah, here. Logistic distribution is basically an S-shaped distribution. Okay, and which is basically nothing but it is representing your probability part. So here you see that it is gonna represent, it as a S-shaped curve. Okay. Now here is your first equation, which is basically your again. This is same what we have what I said. This or both are same, and this is, both of them is basically is your non-linear form of, this is non-linear form of logistic regression. This is your non-linear form for logistic regression. This is your sigma. This is basically representing your logistic regression, and they represents the probability. They returns you probability part. Okay, this and this are same. This can be also written further simplified as 1 upon 1 plus e to the power minus z, where z is beta naught plus beta 1 into x. Both of them are same. Now further, if you look at here, this is represented as, now this one is another form. This is known as logit form. This is basically representing it as a logit form. Log, this is represented as log of odds. That is log of p upon 1 minus p. This is known as log of odds. That's what is written here. Why log of odds? Because odds means this. Odds means probability of success. And this is your probability of success p. So 1 minus p is your probability of failure. One represents probability of success, the other represents probability of failure. Here is your linearity part, logistic regression. This is gonna represent on the y-axis. It is a log of odds. It is a linear relationship curve. So this one is linear relationship. Between features x. So here is your x value. Linear relationship between feature x and log of odds. So it is a linear relationship between feature x and log of odds, which is represented like this. This is your log of odds, and this is your x value. So when you try to explain this, you'll get a line, which is a linear line, and this will go from minus infinity to plus infinity, of course. This is gonna go from minus infinity to plus infinity. At plus infinity, it will go near or closer to label 1, and this will be closer to label 0. This is your beta value. This beta this is your rate of change. Rate of change. So as your log of odds will change, at the same rate, this value will also change. So as your x value will change, this will decide that at what rate your log of odds will be changing. That's how it is decided. Okay, so there are two forms. One is a linear form, the other one is non-linear form. Now let's talk about the errors here. Okay, odd ratio and all we are done. Okay, let's talk about now the error. For that, I'll again walk you through my whiteboard part and let me explain you. Now here comes the value. This is where I can explain you that how logistic regression actually works. So here comes my logistic regression part. Here comes the value. Now logistic regression equation, as you can see that we are having, this is your mathematical equation where z is your single feature value or whether it is a multi-feature value. This is your equation, which is basically your first form, that sigmoid, that returns you this S-shaped curve. Already explained you that how does it work, but what I have not explained you that how these probability gets converted into labels, like how the model will able to predict from the probability value, which is returned by this as output 1 or output 0. So it's very simple actually. It uses a threshold of 0.5, or you can also shift it. Okay, so what you can do is you can actually take the labels part and you can compare, you can check it that okay, we have a label and we compare the probability of success is there for given value of x. Now we compare if this value is greater than 0.5, it will return you output as 1, whereas this is gonna return the output as 0. If your probability value is less than 0.5, output will be 0. If it is greater than 0.5, the output will be 1. We have got the BMI value. Now let's just compare for the as the BMI changes, as the BMI value changes, your as your BMI changes, your probability value of success will also change. Now here comes the linear regression model. Here comes the linear regression model, which is represented as y equals to beta naught plus beta 1 into x. Now here y can belong to minus infinity to plus infinity. This is your linear regression model. Now let's start with y logistic. This is represented as y sigmoid. This is where the sigmoid represented. Sigma of z is represented by 1 upon 1 plus e to the power minus z. If I'll just expand it further, it is represented as 1 upon 1 plus 1 plus e to the power minus z. Probability of success for the given value of x. Now let's take the logit form, which is represented as odd ratio, and this is how the equation is represented: beta 1 into plus beta 1 into x. This is your linear form of the logistic regression, and that's what I have explained you. Now, coming back to the point of how does the error is classified. Error is represented as misclassification here, where you can see that there will be few data point where your y actual, that is actual level, will be not equivalent to the predicted value. This is going to happen. So when your y actual is not equals to y predicted, this is what going to happen. And this is known as a term called as misclassification. Again, I'll tell you, let's say if the actual label was 1, but it got predicted as 0, it is known as misclassification. If your label is 1 and got predicted as 1, then it is correct. If it is 0 and predicted as 0 by the model, then it is also correct. But if it is 0 and got predicted, like in this case, you can see red denotes that actual label was 1 but got predicted as 0. So it is wrong, hence it is misclassification. Now, in terms of statistics, there is only one term which can measure this type of error, which is known as entropy. Okay, you might have heard about this term earlier as well. Entropy is getting used by machine learning model to measure the misclassification in your logistic regression model. Why error? What is entropy? Entropy is measure of classification, or you can say entropy is measure of entropy is measure of entropy is measure of misclassification, or you can also say that it is 1 second. So entropy is measure of what I was discussing, that yes, this model uses entropy, which is a measure of uncertainty, uncertainty or randomness, uncertainty or randomness. Entropy is measure of uncertainty or randomness. That's how the cost function or error function is, which is represented as. So your cost function or error function is represented as, like, you have a classification which uses entropy, which is a measure of error in classification. It is given by cost of h of beta x for given value of y. It's given by minus of y log base minus of y log base. This is natural log of h of beta x for y equals to 1, for label y equals to 1. Similarly, minus of y log of 1 minus h of beta x, which is represented as for y equals to 0. So we have got y equals to 1 and y equals to 0. For them, our cost of function is calculated. Okay. Once we combine it, it is represented as log of h of beta x log of 1 minus h of beta x. This is how your combined error equation looks like. There are other metric as well which I'll be discussing. Now, to minimize the error, it uses. Now, there is a difference. For a regression model, your error curve was represented like this because in regression it calculates batch. The error is minimized in batch, whereas in this case, this is your classification error, which will be for different samples. Okay, we have to check a different samples what is your classification value. So you will be seeing that it is not a batch, but it is represented as uh, stochastic form. Now this means that we need to find the minima out of all these. This is also the minima of the curve. This is also the minima of the curve, but this is your global minima. And this is represented as local minima if you remember the maths part. Okay, so we have local minima and we have a global minima. To minimize it, and we have to reach to this point. So when you see that your error curve is we are going down at a very fast rate, we have to settle down for this point. Okay, now we are not minimizing the overall error, but we are minimizing uh, at a very small step. Now we see that this is how it is represented as minus of y. This is your error function minus of y h of b log of h of beta x. This is represented as This is now there are two equations here. First equation, this is your second equation. This is represented as minus 1 of. This is your second equation. Now when you will combine them, this is how the value will be representing. This is also entropy for label 1. This is for entropy for label 0. When you combine it, it is called as cross entropy. And why cross entropy? Because for y equals to 1, this is the curve. For y equals to 0, this is the curve. When you combine or when you add them, the curve will be represented as like this. Okay. Next, how does we minimize the error? To minimize the error, we start with a batch part where you can see that we are minimizing it at a, you can see that it is minimizing at a regular rate. As you observe, this is minimizing your at a regular rate here. But here comes your stochastic approach. So the stochastic gradient descent optimizes the error. Well, in this case, you can easily see that your data sample, which is mentioned, here minimize the value. See that we are minimizing it at a regular rate. So as you observe, this is how the things look like. That's how the data will be minimized. So we go for optimizing the error. So we see that, okay, this is how the sample will be minimizing the data. So we say that our sample will be minimizing here. Okay, done. That's it. This is all about the logistic regression part. We're over with the theoretical part. Now we'll follow the hands-on session. Any question, by the way, in the theoretical discussion that we had, you can let me know. Anybody have any questions? This was about your logistic regression thing. Okay, looks like the Y classification has a non-convex curve. Because your error will be is not the sum of error that we are calculating. Linear regression represents residual curve because here you calculate the error by y actual by the formula MSE, which is basically sum of error. This is what you use, isn't it? This is what you use to minimize the error. Y minus y hat, and you Sorry for the disturbance. I guess I got disconnected. Yeah, so I was explaining here for classification, it is a non-convex graph because it is not for the batch sample that you are calculating the error. That is, you are not taking calculating the error for the overall value, but you are calculating for individual value. This is for individual label. So there is a high chance that the curve of the error will be not a convex curve, but sorry, it will be not a convex curve with a one parabolic shape, but there will be many ups and downs, or you can see the convex shape will be there. Any other question? Clear? Why this is non-convex? Not, acha, by the way, this is not a parabolic shape, okay? This you can consider that it will be a bowl type of shape or upside down umbrella. So there will be a single global minima in this case because of the equation that it uses, okay? This can be also represented as an upside down. This type of curve could be also there, okay? In every cases, it has to find the best error. Whereas if you see the logistic regression, it is a non-linear algorithm. Yeah, one more thing. Linear regression is a linear equation, whereas this uses logistic regression, which is a non-linear sigmoid function. It uses non-linear sigmoid function, okay? And because it introduces non-linearity, the model output, because of this sigmoid transformation, the error surface will become non-convex. This is also one of the reason why you can say this is a error for a linear function, whereas this one is your error for non-linear function. So there will be multiple local minima, and in this case, the approach or the error that it uses is not a stochastic gradient descent, but it does not uses batch gradient descent. This is used for linear regression, whereas this is gonna be the stochastic gradient descent, which is used in stochastic gradient descent, which is getting used in this case. So we have got the batch that is of linear shape. This is non-linear. Non-linear error curve, and hence it uses stochastic, means it will calculate error for individual sample. So that's why you will see that it will be going for a zigzag path instead of a slope. If you see like in this shape, it will be trying to find out like in the linear regression, I said that there will be a imagine that it will be minimizing, like if a ball is getting rolled on a surface of a bowl, but here it will be minimizing at a rate where the value is So we minimize it. And instead of settle down for here, it will skip and it will further go down, and as it will go for all the samples until it finds the actual minima. So that is where it will able to find the actual minima, and for that, whatever the beta values have been found, okay, it is again going for the same point that ultimately it has to optimize the values of all these coefficients for which the model will give you the best result or best fit result. So beta naught, beta 1, beta 2, all these are different points for which the model will give you the best result or best outcome. Any questions? So hope it is clear. Nothing, it is finding individual value. For individual value, it will find the different error point, and for a point, this is not this is not for overall error, right? This is individual value. So it will look for that individual point which has provided the lowest error. That's how it finds it. This is, let's say this is sample 1, this is sample 2, this is sample 3. So different samples are there. It will try for all the samples one by one, not as a sum. So yes, that's how it will able to find. That's why you can see that there is a random jump here, and the path is zigzag. It is not going as a steep drop like a ball is dropping. This is your gradient descent approach for linear regression. This is your stochastic gradient descent approach, which is used by classification, because you don't minimize for an individual sample, but you minimize it for you don't minimize for overall sample, but you minimize it for individual sample in this case. So different samples will give you different error, and it will keep on finding it until it has found the least value. Yeah, go ahead. Yes, write your question or ask your question. Why it is necessary to use linear equation for sigmoid function? No. One second. I have never used. There are two form of equations are there for logistic regression model. One is sigmoid function and one is logit function. Logit function is this one, which is non-linear, which is linear form, and there is a sigmoid function, which is a non-linear form. So there are two different equations. So do not confuse here. Linear equation for sigmoid function is not there. It is basically we have a sigmoid function which is a non-linear form, which returns S-shaped distribution curve as a response, which will be returning you a probability of outcome for given for at a different point. Whereas if you represent this into a linear form, so linear form will basically will be represented in this way, where it explains that there is a linear relationship between feature x and log of odds. So in this case, this is on the y-axis, whereas here probability of success is on the y-axis for the given value of x. So there are two different forms of the same equation. Okay. Why it is using this form beta naught plus beta 1 into x1? Basically, linear regression is logistic regression is transformed from linear regression. That's why I've written here as well when I was explaining this part. This is your linear regression equation, but logistic regression, which is a classification model, cannot use this algorithm, because this is true for when your y is continuous. But if your y is discrete, then there is a transformation required in this equation form, and this is the transformed version of that equation. This is first version, and this is your second version. One is a linear form, the other one is a non-linear form. That's why betas and all are there, beta 1, beta 2. So basically, logistic regression is transformed from linear regression. That's why they are available. Also, if you will see, a very important thing is that I have explained you that this line indicate the importance of beta in this will be that it will able to tell you at what rate your log of odds should change with change in the x. This is decided by your beta value. So beta will decide the rate of change. This is mentioned also somewhere. That's like, so instead of just the slope of coefficient, which is basically it is gonna be representing that it is a rate of change of probability value as your x value changes. So beta naught, beta 1, x1, beta 2 will decide that of x2, beta 1 will decide of x1, beta 2 of x2, when it goes all the way till beta n into xn. So they are gonna decide rate of change of probability value They decide the rate of change of probability. Okay, so as these beta value will change, your probability value will change. That's the importance of beta in this. Whereas in the linear regression model, it was totally different. In linear regression model, beta was deciding the factor of how the y value was changing. So the rate of change in y was decided by at what rate these beta value with respect to the various features are changing. So two different things. One is changing the probability value of outcome. The other one is changing the actual outcome. Okay. Any other question? Any other question? All right. That's the end of your logistic regression part. We will discuss rest all after 10 minutes. Okay, let's continue here. Should we start? So let's start with our hands-on session on logistic regression. Okay, let's start with the logistic regression model. Logistic regression, and the logistic regression model is gonna use okay, so the data sample data that I'll be using here. Let's take diabetes classification. Okay. Few things that we can copy from the previous part is we can import the libraries or packages that we have taken here. We have imported the libraries. Okay, train test split, of course. Instead of linear regression, trying for logistic regression. Instead of evaluation metric for regression, we will be using accuracy score, confusion metrics, and classification report, and let's import all the warnings. Sorry, let's disable all the warnings by importing warnings and disable warning or ignore warning thing. I just copy the sample data. After importing all the libraries, let's take the data sample from here, which will be sample data from the GitHub. Here comes my data sets. We take diabetes sample. Click on raw. Now let's start with our sample data. Let's read the data set. So second, We'll just read the data set, and let's read it with the help of this URL, which is a raw URL of sample data. We'll just take pd.read underscore CSV and provide the file path, which is a URL path. This data set does have the header, so we can write header equals to true, and it also have the delimiter, which is separated by a comma. That's also available. So continue with step by step. Let us just read the data set. What is this? Header equals to 0. Let's provide header equals to 0 instead of header equals to true or false. Okay, let's just show the few important pointers about the data set, which is header. Header shows first 5 rows. Next, diabetes dot tail, which shows the last 5 rows, followed by diabetes dot shape, that shows the number of records and number of columns. Diabetes dot columns, that shows total 9 columns. This is your list of columns which are available. Okay. Okay, started. Next, so we have got plenty of columns here, and shape showcases that there are just very few number of samples which are available, just 768 samples. As we discussed earlier, the step goes like that. If you are performing a machine learning algorithm, the steps are something like this. I don't know if I have showed you this. The ML flow. Let me just show you that. The flow diagram of ML is something like this. All your machine learning follows the ML flow diagram, which follows this strategy for supervised. Let me tell you, this is not for unsupervised. You take first the source of the data, then you clean the data, you look for duplicate values, you look for missing values, you look for handling the outliers which are present in the data set. Remember, there is one of the hypotheses which is followed by the logistic regression, that there has to be no outliers which should be present in the linear in your logistic regression features value. Okay, like in the linear regression, it expects that there were some assumptions about the model as well in that. Now, once we are done with our handling the duplicate values, missing values, and handling the outliers, once we are done with all this part, then we pre-process the sample data. We scale the data, we convert the categorical data to the numerical format. Then we apply standard scaling technique, which we have learned in our linear regression part yesterday, to scale the data set. Further, we select the features by VIF correlation part. VIF is we used it yesterday to handle the multi-collinearity in the sample data. So we handle them, and once we are done, then we split the data set into train and test, and then this trained sample goes into the untrained machine learning algorithm, and test data goes into this trained model algorithm to return you the model evaluation, model performance, like that. This is how the things work. Okay, so yep, plenty of things. There are now to split the data into train and test. There are two techniques which are pretty common. This is known as cross validation technique. One is train test split, which is a random split of data into train and test, and the other option is k-fold technique. K-fold also I'll discuss as we'll be progressing ahead. Both technique have their own importance. As of now, let's follow what we have learned in our previous cases. In linear regression, the step number 2, or in the flow diagram, the step number 2 is data manipulation part, which is about checking first, is there any missing data present in the dataset? Let's check it. See, many of you uh, first has to test for the presence of null value by the function, as we learned in pandas topic, is null dot some function. This is gonna return 0 if there are no missing data, and it is gonna return your number of samples or number of rows for the missing data part. So it showcases no missing data as of now, but is it actually true? Okay. As I said yesterday, you please run 3 tests to check. Second part is, let's check for the describe part, not the house data, of course. How now in this, there is one interesting thing which you have to check. Look at here in the minimum value column. Number of pregnancy is 0, that's fine. But glucose level of a patient or of a person can never be 0. Blood pressure cannot be 0, skin thickness cannot be 0, insulin value cannot be 0, and body mass index can never be 0. If they are 0, this is actually indicating that your sample data is having plenty of missing data. We're checking here for the null value. Let's go for the describe part. This returns you the statistical distribution of the data. We have got the sample of data as count. We have got the mean value, standard deviation, minimum value, and you can clearly see that glucose, blood pressure, skin thickness, insulin value, and body mass index, they are all 0. Let us just handle the missing data. Handling missing values. So in order to handle the missing data, which is again a part of the same, first we figure out that in this case, the missing data is actually hidden as 0. So let's just continue here with diabetes dot log. Let's take all the column that starts from glucose. Okay, as I said, The error is actually hidden in between glucose to body mass index or BMI, and we need to replace all the 0 by nan value. Hmm. Seriously? Type error. Just a minute. Let me figure out what is going wrong here in this case. Just used it like a couple of days back. Okay, let me try. Actually, let me just see here. Columns. Let's take we start from glucose to BMI. Here comes all the values here. We take here all this value. We take all columns. And we'll just replace it. 0 by np dot nan. Okay, now it's done. We removed or we replaced all the okay. Now we take here my diabetes data with a column of insulin. Now let's replace our insulin value by mean value, and let's take the round off function actually instead of going for this because all the numbers are integers. So it is your 156 value. Let's fill the missing value. Fill missing values in the insulin. With mean value. So we have just replaced it, all the value. by the mean. Okay, this is your one of the technique that we can check to handle the missing data. This is one of the option. So we have got with my handling of the missing data technique. The technique is very simple. Replace missing values by central tendency. What is the central tendency? Mean, median, mode. Mean and median for the numerical data and mode for only categorical data. This is one of the common technique for a numerical data and categorical data that we use. And that's what exactly we are doing here. We have selected all these columns, replace their zero by nan, and then we have got our mean value, and let's just replace or fill the value by the mean. And we are done. Okay, we are done. Now let's take my sklearn part. Now this is a imputation technique which is used to handle multiple strategy data. So we have to handle the missing data, and the strategy is not going to be mean, but we will be taking strategy as median. Okay, you can take mean, median. This also takes so your strategy is to handle missing data by imputation technique, and the strategies are mean, median, or most frequent, which is mode. Now, why we have to apply this? Because there are too many columns which are missing. Okay, if you that is interesting. We have not discussed that. Suppose if I like to showcase you that how many data is missing, you can see that then there are a lot of null columns which are missing. Let me execute it. So earlier it showcased 0, but after this line you can able to see that blood pressure is having, glucose is having 5 rows missing, blood pressure is having 35 records missing, skin thickness has got 227 rows missing, insulin has got 374 rows missing, body mass index has got 5 rows, 11 rows missing. So we are able to handle this 374 missing value. So let's handle all the values. for rest of the columns. For that, imputation technique will be used. Let's take a diabetes day. And in this, you have to take all the columns and we'll apply here imputer dot fit underscore transform with diabetes of column. This will able to handle all the missing data, all the rest of the columns. Now there is no categorical data. These are all numerical. So apart from the insulin where we replace by mean, for skin thickness, blood pressure, glucose, BMI, these are all four values got handled by median technique. This will also do the same thing. It will also find the median value for all the columns and it will do that. It will do that same thing. So missing data handled. Now if I'll check it, it showcases 0. Now this is how we are able to handle the missing data part. Now the next thing, after handling the missing data, let's continue. Some important data analysis that we are supposed to do is we need to check for is there any imbalanced class sample. Let's check it. We take it as diabetes data. This is our outcome and we take here with my diabetes outcome and we apply that. It should be converted to integer type because you see that it is represented as a float type. So once we converted it, let's check its frequency count. You will see something important. See, if I'll check it here as value counts, class 0 is 500 and class 1 is 268. Let's start with my X outcome. Let's start with my distribution. Further, we have got plt.show. This is where you can see that the majority of the sample data in this is a 0, not 1. So this means that this sample, if I'll, so what is the problem here? The problem is that if you will take this data and you will try to fit in, if you will take this data, Now we have taken all this value and you can clearly see that the data is skewed towards class 0. This is a clear-cut sign of a problem of a sample distribution, which is called as imbalanced class distribution. One of the label is the sample is skewed. The majority of the sample is for label 0 and not for label 1. We take here x value, which is represented by, let's drop the outcome, followed by, we have got the y value, and we have got y, which is diabetes outcome as well. The technique that we use is here to handle the imbalanced data is known as a SMART. This is used to handle imbalanced class. So we use it to handle the imbalanced class. For this, the technique that we use is SMART technique. What is a SMART? SMART technique. Let's import from imblearn, and this is your SMART technique. What are we trying to do is we are trying to handle a very simple technique is that whichever sample is low in count, that sample will automatically increase its value by a simple technique of nearest neighbor algorithm. That means to those equal to those sample data, it will be taking neighbor technique and it will regenerate a new sample. So this is your transform feature value, and we have got transform label value as well. Okay, we are applying the SMART technique. Let me define a few in a very detailed manner that what exactly the SMART is doing. So SMART just stands for synthetic minority oversampling technique, which is a popular technique for handling imbalanced data set. Specifically in classification, this is mandatory. It uses nearest neighbor algorithm to create new synthetic sample. Nearest neighbor means, say in this minority class is class 1, so it will use the nearest neighbor technique to regenerate more and more samples, which will be increasing the number of count for class 1 and it will make it equal to class 0. So that's where the SMART technique is used. We start with my value counts. These are all 500 each for label 1 and label 0. Okay, so that's how it has made both the samples equal. Now let's check for multicollinearity. The part is there any multicollinearity in the sample data? So let's go with the same variance inflation factor. Let us calculate VIF for each feature in the data set. So let's continue here with VIF data, and it takes empty data frame followed by, let's fetch all the features, followed by, let's calculate the variance inflation factor value. We start with the shape 1. Let us just split the data into train and test. We start with the split data, train and test. Okay, what this has done? It has shown us the multicollinearity. Okay, sorry, I forgot to discuss. Are there any sign of multicollinearity? Yes, there are sign of multicollinearity. These are like really high value. This and this specifically. This is also very close to higher value. So we could have actually dropped one of them. Okay, maybe this BMI we could have dropped, and that would have been given us the perfect result. Reason being, you can clearly see that trend as a split. Let's take your transform feature. Further, we have got transform label. Followed by the tests. Followed by random state. Now we have splitted the data into train and test, random split, random train and random test. 80% of the data goes into training, 20% goes into the testing. Okay, any question? So new techniques which we are learning, multicollinearity we learned here. The new technique that we learned in this case is that for classification it is mandatory to make all the samples equal. Then only the model will able to work. Smart technique is used. So you need to run this test always. And we also learn about how to handle the missing data. If you are having one or a couple of columns having missing data, then you can simply apply fill in a function. But if there are too many columns which is having missing data, then you should follow the technique of simple imputer, which is imputation technique. This also uses the same technique, but it applies to multiple, this can apply to multiple column at the same time. Okay. Any other question? Just let me know if there are any questions here. And it is written here, no? K nearest neighbor, it is using neighboring technique to generate the new sample. Read the statement here. It generates neighboring, it uses neighboring sample to regenerate the new sample. Means it will use all the samples of class 1 to generate new samples of classes 1, which will make small changes to that label, and where it will make the changes, it will make the changes in rest of the features. So it uses neighboring technique. That's the answer. Any other question? Just copy paste this line. Now let's train our model. We start with my logic model, logistic regression. Then train your model here. Okay, done. We start with my logic model. Dot score. Now for a score, it has to use X test. It's giving us 79% of accuracy. All right. Can we make it better? The question is that. Yes. Let's learn about a term, something called as hyperparameter tuning. Hyperparameters. Hyperparameter tuning is required, which means that here there are hidden parameters. Like one of the parameter is solver. There are different options of solver is there. The algorithm solver should use liblinear, which is a good choice when you have a sample for a small sample data. Okay, the default value is, you can write default value is actually LBFGS. It is LBFGS. There are other options as well, like Newton, CG, like that. You see that these are all options available here. When you go for logistic regression, sklearn, this is their official documentation which tells you, or this gives you the description about. So I'm just sharing this link that you can use it for learning purpose or No, these are all your options which are available. Second option is, so we are going for liblinear. These are other choices, but remember for binary classification, these are the two best options. For multi-class, you can use Newton CG, Newton Koleski, SAG, Saga, all these options. But other options are not for them. We do have other things like C value, which is inverse of regularization strength. Okay, default value is 1.0. You can try some lower value of this. Next is a penalty term. Penalty is used to avoid overfitting in the model. And then maximum iteration is important because, see, just 700 sample is not sufficient. So what you can do is you can iterate the model again and again for the same data set, and this is gonna return you best accuracy possible. So let's check how much it improves. Penalty is there. There are two options of penalty. One is L1 penalty, the other one is L2 penalty, or L1 regularization and L2 regularization. L2 is a good choice for most of the cases. Now we have fitted here. See that the accuracy is a 78.5. Let's try some other technique. Zero point zero 0.01. Let's try with different C values. No, it's not helping. Okay, this is interesting. With 0.5, we got 80% accuracy here. So you can try different combinations of C, and this can result into a best fit model. The higher the score, the better is the model. Approximately, not always true, but yes, approximately that's how you can select. Let's start with the ninth part with classification. We have got classification metric followed by from, sklearn. Now, these are important things. Yeah, we have imported it earlier, by the way. Let's first get the predicted value, which is equals to, we'll take the model logit, model.predict with xtest, model done. Next, let's draw the confusion matrix. Confusion matrix. Let's compare actual value versus predicted value. Diagonal values are your correct predictions, non-diagonal values are your false prediction. Diagonal values are your correct predictions, non-diagonal values are your false prediction. Done. You got here my confusion matrix model. Let's take here SNS dot heat map. Yes, let me show you the. Let me just represent this as a heat map part. Diagonal values are your correct predictions, non-diagonal values are your false prediction. So 83 is your true prediction for 0, 77 is your true prediction for 1, whereas 22 is your false prediction for label 0. So this was originally label 0 got wrongly predicted as 1. That is the 22 indicates. Listen here carefully. 83 is your correct predictions of class 0. That means actual class was 0, predicted as 0. 22 is your false positive. False positive. Why it is false positive? Because actually this sample belongs to class 0, which is negative, but it got wrongly predicted as positive label, so that's why it is false positive. This is true positive again, because actual label is 1, got predicted as also 1. actual level is 1 but got predicted as 0 or your 18. So 18 is your wrong prediction, 22 is also your wrong prediction, 83 is your correct prediction, 77 is your correct prediction. Now let's start with my classification report. Here comes a very important metric here: precision, recall, F1 score, and number of samples. Support first, easy thing. Here is number of samples. Precision value. Precision indicates how many predicted samples, how many out of all the 0 got predicted as 0, and how many of class 1 got accurately predicted as 1. So this is basically, this is a measure to predict how much out of actual sample got predicted as positive and how many got correctly identified. There will be many sample which will be wrongly classified as well. So that is not part of, that is not been included in this. Similarly, let's take one more part, which is recall value. So after precision, we have a recall. Recall is how many of the actual positive are actually correctly identified. That means, so this is predicted positive. This is out of all the predicted positive, how many of them are actually positive? I mean, there are, you can see that if you look at this diagram, everything is calculated from this only. So see, the total number of positive is 77.22. 77 plus 22. These are all predicted positives. But out of this, 77 is your true positive or true prediction, whereas 22 is your false predictions. This is not positive, this is negative actually, right? So recall tells you about that. Next is F1 score. F1 score is harmonic mean of precision and recall. This is used as a metric to balance out both false values, false positives and false negative, because precision will only be telling you about the correct predictions. Similarly, recall will also tell you about the correct prediction, but F1 score balances out. It has to take the average value of both. Okay, done. Okay, we are done here with our classification model. Predict new sample data. Let's start with my new sample data. Let's take here my test sample data. Okay, this will be randomly selected data. We assume that this is our new sample data. So how to use this new sample data? If you want, you can make the changes as well. Let's take this new sample data and let's write here my logistic regression model, which is a logic model to predict this new sample data, and it is going to tell us whether the label is 0 or the label is 1. Okay, label 0 means model predicts that with these configuration of pregnancy 2, glucose 90, blood pressure 80, the person is not diabetic with age 24. This is also 0, so you can continue to run it. That's again 0. Now this is the configuration with glucose being 179, blood pressure 72, skin thickness 42, insulin value 130, body mass index 32.7, age being 36, the person is not diabetic. Okay, we are done. Are we done? Any question? Okay, so that's it for today's session. We are done with this logistic regression model. I cannot see any question here. So once we can see that there are no questions, let's end up today's meeting. See you tomorrow with the next model. Thank you all.